For this piece? So hypotenuse over adjacent, like that, right? Minus cosine, which is adjacent over hypotenuse. I'm there. I'm going to do a little bit more though, okay? Just because, I mean, this is done, box it up, we're happy, all right? But I'm going to do a little bit more. I'm going to multiply this through. So here to here, two negatives become a positive, and the threes reduce, right? It becomes 1/16 square root of 4x squared plus 9, because those threes reduced out, right? Yeah. And then I do here to here. Unfortunately there, the threes don't reduce out. I have a 9 on top. It'll be positive. 9 over 16. And then times 1 over square root of 4x squared plus 9 plus c. There we go. Yeah. There it is. It's a lot of work, huh?
How long should you be able to do this on the test?
I think the next test, it probably only has like 5 problems on it.
Oh, no.
So it gives you about 20 minutes per problem on average, and some of them are quicker, some of them are longer. Is there another question? It's like 5 or 6 problems. Mm-hmm. Yeah. Yes.
How did that first term in the parentheses become negative?
I erased it. We had negative u to the negative 1 on our antiderivative minus u. Then in front, I think we had 3 over 16. Do you see that line?
But how did that first term get
About the 3 over 16 being negative, which you got from cosine.
Are you saying this?
No, like the negative u to the negative 1. Because once you substitute it for u, I had got 1 minus u squared over u. I don't know if that's confusing.
You should have 1 minus u squared over u squared. Because the bottom was cosine squared. Right?
Oh, yeah.
Right? Okay. You see it?
Yeah.
Okay.
How do you make this,
Time-wise.
How do you get faster at doing this?
Yeah, you just have to practice. I mean, it's... Do we want to check it or no? Yes.
So like you factored out the 4, I guess, so you got like the 9 over 4
Yeah.
to start. Can you also just like plug in the tangent theta, 3 tangent theta, whatever for x, bring the 4 out in front, and then when you factor the rest out, you can just bring the 4 in like that, so you don't have like any fractions.
Wait, say again. Can you just do what?
So instead of factoring out the 4 to start with, you
Okay.
just plug in the 3 tangent theta for the x, and leave the 4 out in front, and then you factor everything else out, and then the 4 is still up front, so you can just bring it out and not up the
Are you going to do the 9/4? Are you factoring the 4 out of the 9?
I didn't do the 9.
You gotta do the 9 out, you gotta do the 4 out of the 9 if you're going to do that. I think what you're saying is, can you just leave the 4 there,
Right.
and then
And then
times 3 tangent,
and just 3 tangent theta squared.
and then that thing squared, and then so you're going to have plus 9 like that?
Yeah.
The problem is the Pythagorean won't work, because when you square, if I'm understanding you correctly, because on your next step you're going to have, what, 4 times 9 tangent squared theta, tangent squared theta plus 9 like that. And see, you can't pull a 9 out because of that 4.
Oh, yeah, I missed that. Okay.
But this would work if you did 9/4 here.
Okay.
Then, on this step, sorry, this would be, hold on, back up. You would have to be working on that right there. Then you could do everything you were just saying, you could do it right here. What I decided to do was just go ahead and take that 4 out of the problem completely, because then if I leave it there, I got to keep track of it the whole time, right? So by pulling it out as a 2 and then cubing it, it's just gone. It's not my, it's not part of my nightmare anymore.
Did you say that 2x equals 3 tangent theta?
2x equals, so that is yes, and what you're basically doing is like a u sub first. So, but the method of pulling that out, I think, is important. Like how I pull that, that's why I teach it that way, because I think that, That's more useful for just math people in general, that skill. All right, I've got another one for you. We decided not to check it, right? We decided not to check it? All right, how about this? I haven't done one where we had to do the power reducing yet, but let me get through this first and then. Oops, there's a 1 on top of this. All right. Do you see anything here? Why not? The middle term right here. This middle term, if that middle term wasn't there, then we could possibly see it as being something like this, right? But with that middle term there, that's the first time we've seen something like that. That kind of throws this other layer, this other element of difficulty into the problem, all right? So when you see something like this, we want to eventually get it to this form. We do. So to do that, we're going to look at the quadratic under here, and we're going to complete the square first. All right? So this is a side step. I'm taking 9x squared plus 6x minus 8, and I'm going to complete the square. Why does everyone like throw up in their mouth when I say complete the square? What is the problem with complete the square? Why do y'all not hate it so much? Same thing if I say long division, which I'll say next class. Then everyone's like goes crazy.
They just don't teach it well.
Yeah.
I just never.
It doesn't make sense.
Yeah, never makes sense.
Okay, let's not overcomplicate it. All right. What? No quadratic formula. Okay, regardless of how you've learned how to complete the square, I'm going to present it to you. There is a chance, potentially, that you learned it in a way that is not going to work for you in this class. So I'm just going to present it in a way that, I think you will be fine with it, okay? When you complete the square, first thing you want to do is take a look. It has to look like a quadratic, like a squared plus b squared to c squared. Sorry, what? A squared plus b squared. What am I saying? Oh my God. Ax squared plus bx plus c. You need a quadratic trinomial. Ax squared plus bx plus c. We've got that, yes? Okay, to complete the square, you have to have a coefficient of 1 on your x squared. We do not, right? So I'm going to start by factoring a 9 out to begin. And for those of you who know how to complete the squared, you're great at it. Please note, this is not an equation. This is an expression. So you cannot divide both sides by 9 right now because there is no both sides. All right? There's just an expression here. That's why I must factor the 9 out. I'm going to pull the 9 out, kind of like we did with that 4 in the previous problem. That leaves me with x squared, but I no longer have 6. I now have 6 over 9, which is 2/3. I'm going to write 6 over 9, just so everyone understands the method. So if you need to, make a note for yourself for completing the square. First step, must have a coefficient of 1 on x. So that's, if there's a number here, you're going to factor it out. And all that does is, it just divides each of these numbers by 9. That's all that happens. Let me just clean up that middle fraction. This is equal to that, which is equal to that, which is, this is 2/3, right? X minus 8 over 9. All right, so now we have a coefficient of 1 on this x squared. Right? That's not so bad, right? Not so bad? The next step is, well, this is just, you just are told to do it, and I'm not here to explain why this works. Just do it. You look at the number in front of x. Okay, and you take that number and you write it down over here on the side. And you're going to take that number, 2/3, and you're going to divide it by 2. Now that's the old school division by 2, right? Really what you're doing is multiplying by a half, right? That's the same thing as dividing by 2. So you're going to take that number, 2/3, and you're going to multiply it by a half, which for us just turns into 1/3, right? Okay, you do that every single time you do completing square. Coefficient of 1, take the number in front, take half of it. Always half. Now, that's our first kind of like magic number. When in college algebra, I call it our first magic number. And then we take that number, and what do we do with it? I heard? We square it. So we take that number, and we square it. And we get 1/9. And that is our second magic number. All right? The question is, what do we do with those numbers, right? So I'm going to rewrite the problem. Okay? I'm going to rewrite the first 2 terms, x squared plus 2/3 x, all right? And now here's where everything comes together. You're going to take your second magic number at this point right here, that 1/9, and you are going to add it and subtract it simultaneously. That's a hidden 0 right there, right? That's like a 0, so I haven't changed the problem by doing that, right? If I add something and take it away, it doesn't change it. And then what was still next to this? Because I had x squared, 2/3 x. I still had minus 8/9 back here, didn't I? Was everyone all right with that? So get a coefficient of 1, take whatever numbers here. And by the way, when I said whatever numbers here, if this was negative, I would have done negative 2/3, and this would have been negative 1/3. But it's positive 2/3. So took that number, took half of it, took that number, squared it, took that number, added and subtracted. If you do that, if you do this correctly, then here's what I can tell you. These 3 terms, these first 3 terms right here, are a perfect square trinomial, which means that that factors perfectly to be 2 things that are identical squared. And the thing that it factors to be is that magic number with an x. So x plus 1/3. So you just go back and use that number right there. And you just put it next to an x, you square it. That right there is this. If you don't believe that, right? If you don't believe that, then do it yourself. You can just FOIL this out, right? Here, 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 here. If you do that all, you will in fact get this. I don't like the way I write 1/3. It's that bad?
Yeah.
It's that bad? It's not that bad.
It's bad.
See ya. Take care. That's funny. Okay. All right, so these 3 become this, right? And then this, you can just put together, right? -1, -1. Okay, there's where we are. Let's go back to this. So the big difference for those of you who've seen completing the square in the past and feel pretty comfortable with it is that on this step right here, where I did the plus 1/9 and minus 1/9, in college algebra, a lot of times when you're doing completing the square, you have an equation. So you're told, hey, just add 1/9 to both sides.
Yeah.
Here we don't have an equation, so we can't do that. That's why we have this hidden 0. Add it and subtract it. Add it and subtract it. If we had an equation, then we could do something on both sides, but we don't. So we're forced to do it this way. All right, here's where we are. 1 over, okay, all of that was under a square root, wasn't it? So square root, I have the 9, then I have a parenthesis, then another parenthesis, x plus 1/3, all of that squared minus 1, like that, and then dx. Yeah? That 9 is out in front, this big parentheses right here, right? That 9, I pulled that out of everything. And I can pull it out of the root, can't I? This is multiplication right there. I can pull that out as a 3 and out as a 1/3. So I'm going to do that. Square root of, okay, I've completed the square, yeah. That's where I am. Does that look like one of these now? Which one does it look most like?
Number 2.
The second one? It's like variable squared minus constant squared. So I would agree, it looks most like that, right?
Yeah.
Okay, to continue and make it look exactly like that, I'm going to make a basic u sub. And my basic u sub is going to be x plus a third. Because what's a derivative of x plus a third? 1 dx, which is here, right? So what that will do is that will turn this into a u squared minus 1, and then it'll look like that, and then I just go through the trig sub. All right, so now my u sub, u is x plus a third, du is dx.
I have a quick question.
Yes.
With an integral, anytime that you make a substitution, I don't mean like a u substitution per se, like you take any expression inside of it and turn it into another variable just to make it easier,
Uh-huh.
you have to go through the u substitution process, right? Because otherwise you lose track of what's on the inside. Like in other words, if you say x plus 1/3 and just say that's, like don't do a u sub, but you're just saying that's a squared.
You want to just take that and replace it with a squared.
Right, and just leave that until the very, very end. You can't do that, right? Because you lose track of,
You have to keep a track of the differential.
that's where
That's where the trouble would be. Because if the derivative of this is just 1, then that's fine.
Yeah.
But if let's say this was x squared plus 1/3, then the derivative of that's 2x, and
Then
you're going to lose it. You're going to lose it, yeah.
Gotcha.
That's just kind of scary, right? Because like you could always not be into like there's a lot of room for error. Yeah.
Yeah, a little bit, huh? A little bit.
You get lost in the sauce.
So we've got, I'm replacing x plus 1/3 with u. The derivative of that's just dx. So my new integral becomes 1/3 outside integral 1 over then u squared minus 1, right? That's u, that's squared, that's minus 1, and then dx is du. All that did was just cleaned it up a little bit to make it look like this formula.
So completing the square was the hardest part of this thing.
Yeah, well, we're not done, so let's see where else we got to go. I'm pretty sure the rest is going to work out pretty straightforward, but you know, you never know.
Completing the square again?
Pardon me?
What is completing the square?
It's rewriting the trinomial as something squared plus or minus something squared.
Also, rewrite it into a binomial.
Yes, two things being added or subtracted, but each of those things are squares. So you're completing the square. You're completing. There's a picture that goes with it that's really cool. I just don't have time for it today.
There's three parts of it. You're trying to squish it down to make it into 2 parts.
Trying to make it look different. Yeah.
Okay.
Instead of 3 things being added together, you're looking for 2 things that are squared being added together.
2 things that are squared being added together.
Yes.
Yeah, makes sense.
I can show you a
It's like
picture.
reverse boiling, right? No.
Not really.
Okay, but
Not
close.
really. Close. We'll just say
Close
close. Close. It's still math. I am now going to use this, right? So everywhere I see what, I'm replacing it with what? Everywhere I see u, I'm replacing it with 1 secant. What's that? Yeah?
Isn't this just inverse of cosine hyperbolic?
There's a formula, I'm sure, for this, right? I'm sure there is. Yeah. But I'm grinding this out. I'm grinding it out because we need the practice. We need the practice. All right? There's a bunch of formulas that, but I wouldn't, on a test, I wouldn't count on a problem turning out to be just a formula you go right to. So, but if it does, do it, you know, use it. Okay, so what did we say? We're going to replace what with what? U with, so the u is like the x over there in that formula, right? The u is like the x. So I'm going to go trig sub u, oh, what's a? A is 1, right? Because that's 1 squared. So I go u is secant theta. Okay, derivative. du, not dx, is secant theta, tangent theta, d theta. And then the square root part, right? What would happen if I try and figure out what the square root part is? U squared minus 1. Yeah, it's going to be just tangent theta, won't it be? So I replace u with secant theta, so secant squared theta minus 1, but that's tangent squared. You do kind of get to a point, if you do enough of these, where you don't have to do this square root every time. You just start to remember, every time I do that substitution, this happens.
Oh, okay.
You get to that. I mean, it takes a while, but you get to it. There we go. Rewrite the integral. 1/3 integral 1 over. Okay, the square root thing, we just said turns into tan theta on the bottom. And do not forget the du, right? The du is secant theta, tangent theta. Secant theta, tangent theta, d theta. You can, yeah, you make it fun, right? Make it fun. All right, I am reducing the tangents. I am reducing the tangents, and I'm left with secant theta, d theta, 1/3 out front. Okay, so from here, 1/3 integral, I'm just left with secant theta, right? D theta. Now, if you look back in your notes, we did this, but it's on your formula sheets, so we can use this formula.
Isn't it like an ln?
It's natural log secant theta plus tangent theta, yes. So this is 1/3 natural log. This is the one where I showed you like somebody suffered for a long time trying to figure out this problem, right? That's the antiderivative of secant theta. It's on your formula sheet. And now I'm going to need to know what secant theta is, and I need to know what tangent theta is. So now I go back to my triangle. Where was my trig sub? Where was it? Right there, right? So u is secant theta. I'm going to draw the triangle, even though I may not necessarily need it. I'm going to draw it. I'm going to rewrite secant theta equals u as u over 1 so that I create a ratio. Secant is the hypotenuse over adjacent, so u over 1. That forces this side to be square root of u squared minus 1. I'm going faster now because I'm running out of time, right? I had these two sides from that, and so I solved for the third side. That way I've got the whole triangle. I can answer any question now about any trig thing. Question? Okay, formula, go look, what formula is it?
It's on the last page.
It's 14
Reference page,
on page 6.
reference page 6, formula 14.
Yeah.
And we proved that in class, I don't know, back in the day. Right? You see it? And so I think I'm ready to put this together. This is going to be 1/3 natural log absolute value. Okay, secant theta, that's u, right? Plus tangent theta, which is this over this, right? So square root of u squared minus 1, close it, plus c. We're not done because we got to get back to x. So what was u? Does anyone have a question on these two? Secant is this over this, and then tangent is this over this. So I just slap them in there. I didn't put the ones on the bottom, but what was u? Go back. X plus 1/3. So I'm just going to replace all my x's with x plus 1/3, and I'm going to be done. I don't need that in parentheses, but I'm going to put it in parentheses anyway. Now here I do need it in parentheses.
Okay, so when you do the u sub, you have to rewrite it back as in terms of x.
You've got to get your integral back in terms of x. Whatever variable your integral starts with is what it has to end with. Like your answer has to be in terms of x. I have 10 minutes. I do want to do one more if we can, at least get it set up. I want a problem that works a certain way, so let me look real quick. This will be our last one. I don't know if I'm going to get through the whole thing. I'll at least get it set up. So off topic, on topic here. This is really, like in the future, engineering, computer science, like you're never going to be doing these integrals. Like you're never going to, right? Which is, brings in the bigger question, like, why are we doing this, right? So would you agree, now that you've experienced a little bit of this trig sub, that, this requires some management in your mind about how you proceed through something, right? So this is about developing that part of your brain to think, make sure you can think that way, because engineers, computer scientists, they need to be able to organize ideas and logical steps, put it all together, right? It's way different than Cal 1, right? It's just a different sort of thing. So just keep that in mind. Like, you're never going to do this by hand, but you need to be willing to throw yourself into this problem until you get it, right? Keep grinding away at it. All right, I'm going to move fast because I have 7 minutes. So first thing I'm going to realize here is that this does look like one of those, but I have to realize that the denominator is actually the square root of x squared plus 25 to the 4th power, right? Because that's what it would mean to square something, right? It's the same as taking the square root to the 4th power. You buy that?
Yeah.
Okay, now I had to see that step. Now I've shown you, now you know you can look for that, right?
Oh, that's cool.
Now I can use this formula right here, right? A for us, yes?
Can you explain that a little further?
Yeah, sure. So there's a couple ways to look at it. If I do square root of x to the 4th, I can look at that as x to the half to the 4th, right? Because square root, and then if you do multiply those two, half of 4 is 2. So that's another way you could look at that. And thank you for asking. All right, so now the trig sub. I'm going to let x, thank goodness, so I don't have to complete the square, huh? X equals 5, because a is 5 for us. 5 tan theta, right? Tan theta. Okay, take derivative. Dx is going to be equal to 5 secant squared theta, d theta. And without showing any work, I'm going to just write down what the square root part would turn into, okay? The square root of x squared plus 25, if you work it out, should be, any guesses? 5 secant theta. There we go. So that's going to be all the information from the trig sub. So my new integral becomes 1 over, okay, the square root of all this, right? The square root right there is this thing, raised to the 4th power. So I'm going to write it this way. The 5 gets raised to the 4th, and the secant theta gets raised to the 4th. So that's me taking this, which is that, raising it to the 4th, which is that. And am I done? Dx, right? I need the dx. So the dx is 5 secant squared theta d theta. So 5 secant squared theta d theta. So I kind of like doing it this way because on the next step, I'm just going to say that 5, one of those goes away, and this now becomes 5 cubed, right? 5 cubed is 125. Just a little easier for my brain to handle that. So I'm going to put a 1 over 125 on the outside integral. How many factors of secant reduce out there? 2 factors. So I'm going to have a 1 over secant squared on the bottom. And please don't tell me that the antiderivative of that is 1 over tangent. Right? That's not the way we do it, right? You can't do the antiderivative of top and bottom or anything like that. So, but you can rewrite this as cosine squared. Yes? And now you go back, and I think this is what we were asking about earlier, is how do we handle cosine to an even power? Power reduce. Or the power reducing or half angle, I told you there's 2 different formulas. That's what it is. So for this I go, oh my goodness, come on. 1 over 125 integral. I'm just going to rewrite that as 1/2 parenthesis 1 plus cosine 2 theta d theta. Guaranteed, without question, you will get a cosine squared or a sine squared on your test. Somewhere in some problem, you will have to do this step. It's going to happen, for sure.
I just need to know that that's something that.
Gotcha. The 1/2 comes, y'all know what I'm doing? I'm just using the formula? I mean, you have to go back and look at your notes. We did this.
250.
Yeah. What'd I do? Oh.
Oh, yeah, I was.
What did I do?
You multiplied by 2.
I did not multiply by 2, apparently. 1 over 250. And then here, let's see. 1 plus, I'm almost out of time, cosine 2 theta, d theta, 2 minutes. All right, I'm going to now do the antiderivative of each one of those. So no more integral sign. And I'm doing the antiderivative with respect to theta, right? With respect to theta. So this is just theta. And then here I have to take care of that chain rule. So 1/2 sine 2 theta plus a constant. It's my antiderivative so far. And I've got to get everything back to x, right? And I run into a little bit of an issue here. Because when I try and get back to x, if I go back and look at my, I'm going to erase the original problem here. If I look at my trig sub, the trig sub I had was x was equal to 5 tan theta, right? And if I create my ratio x over 5 equals tan theta, then my triangle looks like this. That's my triangle based off the reference, right? The trig sub. The problem with that triangle right